Okay, here we've got Quincy the Quadratic, part 3. This is where we're going to put it all together. If you remember or watched the previous parts, we found the first derivative and the second derivative to find critical points. That helped us tell whether the function was increasing or decreasing, the first derivative, or whether the function was concave up or concave down, the second derivative. Out of all this, I'm going to put everything on one sign test, the derivative and the second derivative. You can look either in the reading or in the previous parts to see how this was done. At x is equal to 1, we had our only critical point. Here the derivative went from positive to negative. The second derivative, if you notice, was always negative, so I'll put two negatives down here. Now what does all of this mean? Well, we're going to take a look at this. In the lab, we talked about what different pieces look like of a function. And there are 4 different possibilities based just on what the first and second derivatives can do. If the first derivative was negative and the second derivative was positive, we get this little piece right here. If the first derivative was positive and the second derivative was positive, we get a piece that's shooting up like this. If the first derivative was positive and the second derivative was negative, we get a concave down piece that's still increasing. And if the first derivative was negative and the second derivative was negative, we get a concave down piece that decreases. So, if we look at what our sign test was for this function, we have our first derivative positive and our second derivative negative. Well, in that case, our piece looks a little something like this. It's that little hook that has a concave down piece that's increasing. Similarly, we have our first derivative negative and our second derivative negative here, so we use this piece that goes in the opposite direction but is still concave down. We also need some important points because this will help us draw the picture here. We know at our critical point x is equal to 1, we can plug in 1 to find the value of the function is 5. Our y-intercept is obtained whenever we actually plug in x is equal to 0. When we do that, we get the value of 2. Our x-intercepts are a little more complicated. In this case, we're going to plug in to our quadratic formula. And when we do so, we're going to get 1 plus or minus the square root of 15 over 3. All of that's worked there on the paper. Putting all this together, we get a nice picture of what this function looks like. We have a relative maximum at x is equal to 1. Well, why do we have a relative maximum? We have a relative maximum because the derivative changes from positive to negative. In addition, we know that our second derivative at this point is equal to negative 6, and our first derivative was equal to 0. We put our intercepts on there. We've got 1 plus root 15 over 3, comma 0, and 1 minus root 15 over 3, comma 0. And we also put our y-intercept as 0, comma 2. So again, if we have to justify that we have a relative maximum at x is equal to 1, we would say because f prime goes from negative to positive. Oh, no, who's saying that? No, it goes from positive to negative. Or we would say f double prime is less than 0 and f prime is equal to 0 at this point. So we got 2 different ways that we can justify this. Relative maximum, we could use the first derivative test, which states that if the derivative goes from positive to negative, we have a relative maximum. Or we can use what's called the second derivative test, which would explain that our second derivative is less than 0 and our first derivative is equal to 0. Either way is an appropriate justification, and the way that you use depends on the information that you're given.